This is AI Podcast. I'm David, your commentator, and with me is Maya. Today we're unpacking a paper called Language Agent Tree Search, or LATS, which aims to unify reasoning, acting, and planning in language model agents.
Hi everyone, I've been looking forward to this. David, can you start with the short version? What's the key takeaway?
Sure. LATS weaves Monte Carlo tree search into a language model agent, so the model proposes next steps, evaluates partial ideas, and reflects on mistakes while using real feedback from the environment. With that unified loop, it outperforms popular prompting and search baselines on coding, interactive question answering, web navigation, and a math puzzle, often without extra training.
So it's not just reacting to one prompt. It's thinking ahead, trying options, checking what happened, and then steering based on evidence.
Exactly. It's deliberate rather than purely reactive. The representative author is Zhou from the University of Illinois Urbana-Champaign, and the work appeared at ICML 2024.
Great. Give us the background. What problem are they fixing?
Common prompting, like chain of thought or react, tends to follow a single path. If that path drifts, errors compound. Search-style prompts explore multiple paths, but often do it in isolation from real feedback, as if the model's story about the world is enough. LATS targets the gap by making reasoning, acting, and planning reinforce each other inside one framework that pays attention to real observations.
Got it. How does LATS actually work?
Picture problem-solving as a growing tree. Each node stores what the model has thought, what actions it took, and what it observed, like a web result or a unit test failure. From a node, the model can branch by adding a thought or by taking an action. LATS uses tree search to decide which branches to expand next.
Where does the model's judgment come from in that loop?
2 places. First, the model proposes candidate thoughts and actions. Second, it scores partial states to estimate how promising they are, and it pairs that with a self-consistency signal so the search doesn't chase noisy hunches. If a branch fails, the system prompts a brief reflection about what went wrong and how to adjust, and that note is fed back into the context for the next steps.
So it's proposing, judging, and learning on the fly, and it listens to real feedback. How does it choose which path to follow?
It borrows the selection rule from Monte Carlo tree search, which balances exploring new ideas with exploiting promising ones. That's the planning piece that keeps the search disciplined.
Where did they test the idea?
4 settings. First, interactive question answering with access to Wikipedia search and lookup. Second, programming on human evil and MBPP, where the agent gets compiler and unit test feedback. Third, web navigation and shopping in the web shop simulator with long, messy instructions. And fourth, the game of 24, a compact math puzzle. They compared LATS to strong baselines like chain of thought, self-consistency, react, reflection, tree of thoughts, and RAP, using commonly used models at the time, including GPT 3.5 and GPT-4.
All right, results please, but let's keep numbers light so it's easy to follow.
On coding, LATS raised pass-at-1 scores substantially. With GPT-4 on human evil, it reached around 93%, and with GPT 3.5, it also made a clear jump over react and reflection. On interactive QA, combining reasoning and acting within LATS produced the best exact match accuracy in their setup, landing in the low 70s. On WebShop, it achieved a higher overall shopping score than several trained policies, even though its strict success rate still trailed a fine-tuned agent. On the game of 24, it was the strongest among the compared prompting and search methods.
So the pattern is consistent. When a task benefits from trying ideas, reading feedback, and steering with a plan, LATS gets more right.
That's the author's interpretation. They also note that, relative to other tree search variants, LATS tends to expand fewer dead-end branches thanks to the value estimate and reflection, which guide exploration more efficiently.
Do they share the code and prompts?
Yes. The repository is public with prompts and many logs for the programming runs. Large weblogs are available on request because of size.
Before we get too excited, what should listeners be cautious about?
First, sample sizes. The interactive QA and web experiments use modest sets, on the order of dozens to 100 examples, which are fine for controlled comparisons, but not a production-scale stress test. Second, compute cost. LATS is heavier than a single prompt because it proposes, evaluates, and reflects across multiple branches. That cost can be acceptable for high-value tasks, but it isn't free.
And what about assumptions in the environment?
LATS works best when you can roll back to earlier states, like in a coding sandbox or a simulator. Real systems with irreversible actions or partial observability need extra safeguards or a world model to simulate outcomes safely. The value function relies on model judgments, which can shift as models update, and external APIs can change, so reproducibility needs attention.
Makes sense. Why does having the model score partial ideas help so much in practice?
Think of how people work. We don't write one solution and hope. We sketch several, toss out weak ones early using quick checks, and refine the promising path, guided by tests or evidence. The value function is that early triage. Reflection is the notebook that captures what failed and why, so we don't repeat the same mistake.
If I'm a practitioner, when should I reach for LATS?
Use it when wrong answers are costly, and when you can get reliable feedback from the environment. Software tasks with real unit tests are a great fit, as are research-style web tasks where you can verify sources. For quick, low-stakes outputs, simple prompting is cheaper and often good enough.
What future directions stand out?
Several. Reduce cost by distilling the value function into a lightweight verifier or critic. Make search adaptive, so it explores more only when confidence is low. Handle irreversible environments by integrating an explicit world model or simulator. Strengthen evaluators with domain tools, like static analyzers for code or retrieval-grounded checkers for QA. And finally, scale to longer, multi-goal workflows or even multi-agent settings to test performance over long horizons.
Before we wrap, give us a concrete picture from the coding setup.
The agent writes a draft function, runs tests, and sees failures. Instead of starting from scratch, LATS reflects that the issue looks like an off-by-one error, spawns a few targeted fixes, scores each option for promise and agreement, and tests the best one. After a few cycles, it converges on a passing solution. It's not random edits, it's a guided search informed by evidence.
And on interactive QA?
Similar idea. The agent explores multiple reasoning paths, searches and looks up pages, checks whether a candidate answer is supported, reflects if evidence is thin, and then consolidates on a better supported answer.
That makes it feel less like a prompt trick and more like a disciplined workflow.
Exactly. Final verdict, LATS shows a practical way to unify planning, acting, and reasoning in language model agents. The improvements across diverse tasks are compelling, though the compute cost, modest evaluation sizes, and environment assumptions mean it isn't a universal drop-in. It's a strong template for feedback-rich, high-stakes problems.
Clear and helpful. Thanks, David.
Thank you, Maya. And thanks to everyone listening. This has been AI Podcast. If you found this useful, share it with a friend who cares about making language model agents more reliable. See you next time.